This conference will now be recorded.
Yesterday we had a small discussion on natural language processing introduction, and then some of the techniques. We had a discussion about pre-processing techniques, how to pre-process the text data so that it could be represented in a better way in the computers for the further analysis is what we had a small discussion. So to wrap up those pre-processing techniques, so they are like cleaning the data is the basic step, what we do in other data also. Other than that, here tokenization is a very important step wherein the text data is going to be converted into a meaningful format. Here it could be converted as a feature vectors. And then cleaning would require these many steps like removing capital letters, which I don't want. I want to process with the small letters or a different set of punctuation marks. We could find it in Twitter data. So those could be removed. And most of the time we would get a lot of numbers. Those numbers can be removed in cleaning process. And some of the words which we don't consider as a feature for further analysis, those words are called stop words. I, we, me, these are all some of the set of stop words. So those are stop words which cannot contribute much to the feature vector. So we don't mind in removing such stop words. That could be seen in the code maybe in next few minutes. And then stemming is one such process wherein we just remove repetitive words, parts of speech or parts of tagging that we'll see today. And lemmatization also we had a discussion yesterday. Lemmatization which allow us to do vocabulary and morphological analysis, wherein if we have a word called run, runs, running, ran, all would be giving the same meaning. So we would consider all these as a single feature called run alone. So this kind of inflectional forms would be taken care by the lemmatization and the stemmers. So stemmer is the module in which we would cut down the base form and then we take only the base form for the feature analysis. And there are multiple stemmers available in Natural Language Toolkit library. Some of them are listed here. Porter stemmer, which was very old, and the Lancaster stemmer, which is added in the year of 1990s. And the Snowball stemmer, it is a kind of non-English stemmers wherein we find other stem words for the other languages. WordNet lemmatizer work based on the WordNet lexical database, which is available online. And a demo, if anybody of us would like to see some of the text pre-processing demo, it is the stemming demo alone. It is available in this site. You could look at that. And if we compare what is Porter stemmer and Lancaster stemmer, it produces even shorter stem because it runs on many iterations over the stemming what was occurred previously. So we would go ahead only with this Lancaster stemmer, which is newly added. We'll see this code one by one in the Python environment. This was happened yesterday. We had a discussion on tokenization. So tokenization allowing us to splitting the raw text into small in individual units for the further processing. If you would like to divide them into individual units, maybe these units could be either words, sentences, or n-grams. This is quite new to us. Gram is nothing but a single word. So if I say 1 gram, which represents only one word. If I say 2 gram, it represents two words. When I say trigram, 3 words. Why am I saying grams as trigram, bigram, or n-gram in the sense? See, depends on the number of words representing one object, this gram is going to change. Let's say United States, if we represent US or United States, both are going to represent the same object. Similar way, yesterday I had told you one of the other example like corner ice cream house. So here, if we divide them as individual words as individual tokens, corner ice cream house. So it's going to be corner as a separate token, ice cream as a separate token, house is going to be a separate token. So if we are going to divide them as individual tokens, we would not get a meaningful object there. As a human being, I am representing house, corner ice cream house is a single object. So wherein I need to go for trigrams. Trigram will allow us to divide the paragraph into triple words. Maybe the words which is adjacent to each other, maybe triplet would be considered as trigram. When we see examples, we would better understand n-gram. So gram is nothing but a single word, wherein if we connect two words, then it will become a bigram. If we connect triple words, then it will become a trigram. Where it goes on, when we connect multiple grams, it will become n-gram. So when we would like to go for discourse analysis, wherein if we combine multiple words only, then we could get a meaningful sentence. That time we would use n-grams as an analysis for tokenization. So other characters defined by regular expressions. So as we all know what is a regular expression, it will allow us to find out a particular pattern in the given text. So it's a kind of identifying a substring what is available on the bigger string. So regular expressions, there are a lot of functions. So this could be handled as a separate session. Maybe in the next session, I would like to handle regular expressions. There are certain listed set of functions. Each function has a meaningful extraction of expression from the entire text that we'll see in the next class. Other than that, these are all set of methods will allow us to do tokenization. Maybe depends on the type of unit you would like to divide them into individual tokens. We can use either word tokenization or sentence tokenization or n-gram tokenization. So if you see the code here from, maybe you could use import directly, import NLTK, tokenize is the module from which word tokenize or sentence tokenize, both we could use, or n-gram we could use. So if you type import, we would see maybe word, if you start typing, you could see that module which comes with a certain functions to do word tokenization. See, the text what I have given is small text. It includes all the punctuations and other things also. You can apply some of the cleaning methods to remove all the punctuations like this dot and exclamation mark and this quotes, everything we can remove. And then we can apply word tokenizer to individually divide all these into individual tokens. So our output of this function could be like, hi, Mr. Smith, I am going. So all these will be divided into separate token. Sentence tokenizer is similar like the previous one, wherein we could use a module called sent tokenize. This also is a module included in the tokenize NLTK library. Here, before the full stop, it would be considered as one sentence. After the full stop, it would be separated as a different sentence. So sentences are going to be considered as individual features or tokens. And if you see n-gram, n-gram is simply a sequence of n words. Example of grams are given here. If I am representing one word, maybe we don't need a gram concept at all. We can directly go to word tokenizer because individual words are going to be considered as tokens. So when we connect 2 grams only, then we could go for n-gram concept. So here San Francisco, which would not be divided into two tokens, maybe we would not get a correct meaning of it. Because if we divide them into 2 tokens, then San could be considered a different name, Francisco could be considered a different name, wherein it represents an individual object. So we would lose the concept of individual object. So if the 3 musketeers also, again, it would need to be considered as a single object, wherein it consists of 3 grams in it. Maybe she stood up slowly is a 4-gram object. So like that, we can classify them into different gram concepts. This is also one of the important concepts in tokenization. So maybe if we look at, I am using Anaconda Navigator framework. The editor what I am using here is a Spider. If you look at Anaconda, and people, those who have used Anaconda Navigator, it looks like this, wherein we can create a community also, people towards we can work, and then learning we could do. And there are a lot of environments here. We can try out with other environments also. And if you look at the home, you can even go for Jupyter Notebook, Jupyter Lab, even R Studio is also there. We can try out. So it's just a distribution framework wherein multiple people work as a community for development. So under this, I am using this editor Spider for Python development. So pre-processing steps, I'll just start explaining the code what I was using it here. The library which you would need to include under this platform is NLTK. So to import that library, I just used a keyword import NLTK. And Punkit is another library which will have all the supportive functions for a word tokenized module and sentence tokenized module. So if you type nltk.download itself, you can mention this package, and then it start downloading all the relevant modules and functions for that. And from NLTK, I'm just using tokenize as the concept. Import, if we have all the NLTK components, you can see under this. And import what tokenizer I'm going to use. Tokenizer, what I'm going to use here is word tokenizer. My text is equal to the whole sentence is given. So after which, if I am printing, it will show as the individual tokens. Hope everyone had done small exercises in Python. I'm directly selecting it and control enter. I displayed all the individual tokens here in the console. If you look at hi as a separate token, Mr. Smith, everything become individual tokens displayed at the right hand side. If the package Punk is not installed, maybe in the console you would get a request or a warning saying that try installing Punkit in your system. That we can do. If you look at the second code for sentence tokenization, from the same NLTK, I have tried with a different tokenizer called sentence tokenize. So wherein it is going to be display the sentence, the list of sentences as tokenized. The tokens are high. I'm going to buy. This is going to be separated to a separate one, and then this is going to be a separate thing. When we run big paragraphs, you would see the different. In gram, we will list the 2 grams. What I have given here is only 2 grams. It's going to be 5. See, from NLTK, ngram is the tokenizer which I'm going to use. My words were tokenized from my text. I'm just taking, and then I am trying out with 2 grams. So if I use ngram as a method, I am listing out all the ngrams from the my words variable. This my words variable is going to have all the words tokenized from my text. If you see that my text, what I have used here is the text, and that text is going to come over here. From that, I am doing a word tokenize, and then that could be stored in my words, and then I'm going to list out all the 2 grams. So my words, if I give 2, it is going to give us 2 bigram for this. I can just display and show if you look at it. If we see the output, we could feel the difference. See, starting from the first word, I and Mr. is going to be combined as 1, 2 word. And then again second with third, third with fourth, fourth with fifth, like that it goes on constructing bigram. See, why this bigram is constructing from 1 to 2 and then 2 to 3, 3 to 4 like that. Why can't it start with 1 to 2 and then 3 to 4 and then 5 to 6? When you are going to form a meaningful sentence or a meaningful information out of the given sentences, you may miss out some of the bigrams if you're not continuously connecting. That's the reason it is taking all the bigrams starting from 1 to 2 and 2 to 3, like that it goes on. This is called regular expression um, tokenization. Regular expression tokenizer is the module which I'm using it from
Sorry to
NLP.
interrupt you.
Yeah, yeah, please go ahead.
Yeah, see, you have used word tokenize before using
Yeah,
n-grams. So
yeah.
can't we use directly n-grams on the sentence itself?
On the sentence itself, see, we are not importing here tokenize as a keyword here. Tokenization is the process, first of all. Hello,
Yeah, yeah.
are you there? Maybe if we use tokenize and ngram, I have to check. Can
Yes.
I check it and let you? Okay. Because I didn't, tokenizing is
Yeah,
a
okay.
process wherein ngram method which is going to be applied on top of it. So I'll just try out by applying tokenize directly here and then let you know this doubt. Okay. Shall I
Okay.
proceed?
Thank.
Okay. And this is also a kind of tokenizing, regular expression tokenizer. The same text which I have used here. This is a simple regular expression which was mentioned. So it is going to remove all the white spaces from the given text. See, similar way, regular expression would allow us to find out any kind of pattern in the given text. Maybe these word tokenizer, sentence tokenizer, ngram or anygram tokenizer will allow us to go with a predefined format of tokenization. But regular expressions will allow us to identify a particular pattern and then do tokenizer on top of that pattern basis. So as we all know, maybe those who worked with Python might be knowing about what is regular expression. It's just identifying the pattern what was available in the given text. So any pattern, maybe if I would like to find out or tokenize a word which start from zero, or a word which start from always plus and zero, a word which would always start from minus and then O. Similar like that, if I would like to do any kind of pre-processing tokenization using regular expressions, possible. Other than that, these engrams and word sentence, all those tokenizers are all kind of predefined method, wherein you need to apply those methods to find out words, either sentences or grams. But regular expressions are the flexible ones. Maybe we can make use of according to the pattern what we would like to tokenize. And then here maybe I just try out with the words which is only capitalized. If you look at it, the capital tokenizer, the word starting from this slash W indicates it's a function. When we discuss regex, regular expressions, we would better understand it. So a word would start with a capital A to Z. So if you run this, maybe it could identify the tokens which are all starting from capital letters. So similar way, we could try out our own or customized kind of tokenizer according to the way we wanted to using regular expressions. So regular expression itself is a separate a concept which need to be taught in Python. And some of the other pre-processing techniques, what I have tried in a separate script file. These two script files, maybe I would share it with you. Here I just used simple string processing things we might have tried with other languages also. RE is the library will allow us to import all the regular expression functions. So import string, the string class functions I have just included. So sub is just a string class function wherein which allow us to extract the substring from the main text given. The same text only I have used here. So clean here I'm just trying out replacing the punctuations with a white space. So I don't want to use the same punctuations as it is in my script. So I'm just replacing with a string with a empty space or a white space. And so this is converting them into lower. So this we all would be familiar with. not required any explanation. And then some of them, if you would like to remove the numbers, D/D, a word which starting from D digit or ending at a digit. So removes all the words containing digits. So this is also a simple expression which is already given as a separate function in regular expression. This also I'll explain a little bit, but that's the meaning of it. Slash D represents an escape sequence of representing a digit. So this is the reason, maybe this is the reason where when we represent path of a file, we don't use this slash because it is meant for regular expressions. Even in R as well as Python both, that's the reason I am also feeling that we will not represent the file path with a backslash. We will be representing with a front slash because regular expressions has a specific meaning for these escape sequences. And maybe this is the step for removing the digits. And to show the stop word, this is new to us. In English, what are all the stop words are already available? If you look at the syntax from NLTK corpus, which I have told you already, it's a word-wide dictionary. From this, we would know that which are all the words or gives positive meaning, which words are all giving negative meaning, which words could contribute to neutral meaning. Let's say if we are doing Twitter a sentiment analysis about a product review or a particular politician, the tweets whatever people are giving, we can just extract it using an API into Python platform, and then those could be converted as, maybe if a person and his tweet can be converted as a data frame. From there we can extract each data frame cell, and then we can do some of the pre-processing techniques. We can identify individual tokens, and from that tokens we can identify which person have positively given a review, which person have given negative reviews about the product or a politician. So those words, we must know that which are all the words give positive meaning. Correct? We don't know, and that gives the exact answer from corpus. Whenever we would like to see the meaning of a positive or a negativeness and how much percentage it is, we always need to refer corpus. Corpus is just a universal dictionary. It will allow us to identify the certain words which is already defined with a meaning. So if we run this, it shows us these are all the some of the text which would be treated as stop words. Yesterday we had a discussion about feature vectorization also. Once we remove the stop words and then done with some pre-processing technique, we would convert each individual tokens into meaningful feature. So learn is just a package. From there, we are going to follow a method called feature extraction, the text from that text. And what is the feature extraction method I'm going to use? I am going to count the number of times the same text is appearing or a token is appearing. So count vectorizer is the module which I'm importing it for counting the number of vectors. So this we all know, like in packages imported pandas to have different kind of if you look at my text. So after removing the stop words, I am referring the stop words. What is given here is English, and fit to transform is just a method. Just fit and then transform all the vocabularies into vectors. So, and that vector, whatever is formed now, is converted into a data frame. For that, pandas is helping us. So that data frame, which is converted as a name. If you look at the code and the output. See, after removing the stop words from this, if you look at, these are all could be stop words. Hi is a stop word. I am is going to be a stop word again. The output or the feature vector, what is considered here, Some of them are displayed here: black, white, cucumbers, eyed, and there are many more which is not displayed here. And these 111, all these indicating the feature, how many times it is appearing, Smith how many times it's appearing, store how many times it's appearing. So that's what count vectorizer does. It is going to give a count how many times the particular word is appearing in the given text. So I just converted into one row and 13 columns are there. Some of the columns are displayed here. If we have a word maybe twice, vegetables, I'm typing some over here again. So I'll just execute this. Some other word I will try. If you look at the count of vegetables is increased to 3 because I have just added 2 things. I understood why some hasn't come. Some could be considered as a stop word. Maybe it could be removed from it because I didn't check how many stop words are there in this. We can print a stop word separately and then check what all removed out of this text also. When I give assignment, I'll just give these simple kind of text and then give list of things to do also out of it. And about stemming, there are a lot of stemmer as I said. So Lancaster stemmer and Porter stemmer is given. And if you look at the drive, drives, driver and driven, all could be considered as a simple word called the drive. So the stem could be like whatever you give stem, it would give you the right base word or the root word we could say. For drive, it could be drive only actually. And then you run these two. You could see the difference between Lancaster and Porter similar because it was running on the output again iterations. That's what I have shown you as a difference. It would do further level of stemming process. That was the difference between Lancaster stemmer and the Porter stemmer. So Lancaster stemmer produces even shorter stem than Porter because of iterations and overstemming is occurred on the output level. So we could use the Porter stemmer as the right stem for identifying the better word. Next important thing called parts of speech tagging. What is part of speech in languages? Maybe we can just go ahead with what is parts of speech. In English itself, we might have studied about parts of speech called nouns, verbs, adjectives, and understanding all other components what is mentioned these. So available parts of speech tags from how to check in the help file is given as a code nltk.help, and what are all the tag set available in English as a part of speech are given here. If we represent GT, it's a determiner. Whenever you use JJ represents adjective, VB represents verb, and the POS process building. And these are all some of the parts of speech tags which is already defined from English and it's kept as a tag set in the NLTK tool. So it could be represented as a tree when we do parts of speech tagging. So if a sentence is given, maybe subject, verb, object, subject, verb, adjective, subject, verb, pronoun, like that, we can divide and show as a tree structure. Now, if we learned about the top-down parsing and bottom-up parsing in compiler design, maybe we might have learned this parse tree already. And how a parse tree look like also, I'll given example. So in parts of speech tagging, word tokenize is used. Then POS tagging is what we are deriving, or we are just inheriting the module from NLTK tagging. And the text what I have used is James Smith lives in the United States. So for this sentence, how POS is used. So I am just going to show you how a parse tree look like. Take some time to construct. Some of the words like James is a noun phrase, Smith is also noun phrase, live is a verb, and then in is a the is a determiner, united is noun phrase, States is a noun phrase again. So dot cannot have any POS tagging, which is given. This is the parts of speech tagging. When do we use these parts of speech tagging? Let's say in a given sentence, I would like to understand the meaning of the subject from the first sentence to next sentence. I want to relate. So if the subject is just already spoken in the first sentence, which is referred in the second sentence as directly it, maybe in this sentence, if you look at James Smith lives in the United States, and in the second sentence, I start writing he directly. He run a business called something, some business X he has given. So this he indicates what if we divide them into different tokens or sentences, we need to say who the he is. So that he could be referred from the parts of speech tagging from the previous sentences. So POS will allow us to identify the different objects in a better way and give a meaning for them. And this is also like compound next simple concept named entity recognition. This we would see little late also. I'll just brief what is named entity recognition. In a longer text or in a document, there are a lot of entities will be there. Entities called as tokens here. There are a lot of tokens given in the given document. So each token, maybe if the token, if the sentence is given like this, as a human being, I can relate James Smith as a person. Lives is a verb. United States is a country name. So how am I just interpreting these as names, verb, and then country name? There must be some entity for that which is universally accepted. So these entities are already defined as person, people, places, time, depends on the words spoken or words written in the given document. These entities can be recognized easily. So named entity recognition as a concept in NLP will allow us to identify the different entities what is present in the given text. Entities are nothing but people, places, time zones, and many more are there. We could refer when we see that concept in detail. So this could be taught little later, how a named entity recognition can be done. This is a compound term, multiple word extract as a tokenizer. If you see that you all are the greatest students of all time, wherein we have complex words, that could be extracted as a compound term extraction. So among these two pre-processing techniques, we have learnt about tokenization completely with the use of word tokenizer, sentence tokenizer, and engram, and then regex small function. It rejects what all the different functions are there, and other how do we apply this regex with different expressions can also be taught in a separate class. And in the second pre-processing, we have just learned about some of the string functions which could be used as a pre-processing technique in text, like removing punctuation marks, removing capital words, removing small letter words. So that according to our wish and the customization, we can do pre-processing technique using simple string processing methods also. And other concepts like POS tagging. POS tagging is nothing but parts of speech tagging, wherein we could assign the parts of speech for the given sentences like noun, pronoun, subject, verb, phrase, then pronoun, then noun phrase. Everything we can assign using parts of speech. And named entity recognition is a concept in which we could identify the different entities what is present in the text. Entities are nothing but maybe people, places, time zones, and many more. Fruits category, vegetables category, all those. So if a word is given, if you would like to identify what type of entity is that, we can use NVR as a concept in NLP. So to quickly run through, this is just an example. Some of the examples of named entities present in the text are people, organizations, even maybe the company names also we could identify. Phone numbers we can identify if it is represented with 3 units of 3 3 4 units of division, and email IDs must have at symbol over that. Like that, it could identify a lot of entities in NER. As a recap, so these are the things what we have seen today. With this misspellings, different languages also we could try with simple text processing. So I just forward the codes, and then I would like to take up some more questions on it. Next, we will go on how to check the text similarity measures. Anybody have any questions? Since there are no questions, we will move further to text similarity measures. What is text similarity measure? If I would like to check whether these two words or sentences are equal, the meaning is equal. As a human being, when I see that itself, if the sentence is written active voice or a passive voice also, the meaning would be same, isn't it? Maybe the book is bought by me, I'm giving, or I bought the book. Both are giving the similar meaning as a human being interpretation. But in the system, we would not get then if the sentence is written in a different parts of speech. Let's say if it is given an active voice or a passive voice also, it may not understand the meaning because it's going to divide them into tokens and then process these vectors. So in that kind of process, text similarity measures are helping to understand whether two given different sentences are equal in the meaning or not. To understand that, text similarity measures are helping. So text similarity measures are the metrics which will allow us to measure the similarity or the distances. It also uses distance measures which we might have studied um, in other machine learning methods itself. So, but this is going to be run on only two streams. It can be done on surface closeness called lexical similarity, or meaning closeness called semantic similarity. So lexical word similarities and lexical document similarity is one and the same. Lexical word similarity, many applications are there. Maybe similarity between the documents we can check. When we go for information retrieval, are the document which we have retrieved and the one what we are expecting both are same. That way, information retrieval engines are using similarity measures based on the text search, and I would like to classify a set of news into different text, so that text classification can be done using lexical similarity. Document clustering, multiple documents are there, I would like to cluster them into different 1 2 3 like that. I wanted to group them based on some words that can be checked using lexical similarity. Topic modeling, topic tracking, matrix decomposition, these are all some of the applications we could do using these methods, lexical similarity and semantic similarity methods. So this is basically will allow us to identify the similarity between the sentences spoken or the paragraphs spoken or documents what is written. So word similarity, distance measure, what we use is Levenshtein distance measure or edit distance measure, we call it as. Most of the spell check and speech tokenization and plagiarism software is also using this word similarity. So this is most popular. Earlier days, we were using only the text-based matching, but now it is going to understand the word similarity in the meaning level or semantic level, and then it gives us whether how much similar both the documents are, how much similar both the sentences are. We can understand. So the one of the most popular application which uses words similarity is plagiarism detection softwares, maybe Urkund, and these are all some of the examples wherein the article of one person, if it is already plagiarized from someone else, we could identify and how much similar it is. So for the research purpose, people are using this plagiarism detector as a word similarity measure. And document similarity, it runs based on the count of the vectors and based on one more term called document term matrix. We'll see what is document term matrix. Bag of words is also there in text mining of R as well as in Python. Bag of words in the sense, if I have a set of words, maybe word cloud when we form. So the most frequent words what it form or the it is going to represent a particular term is what bag of words indicate. Cosine similarity is one such measure what we use to identify the document similarity. If the cosine similarity is more than 80%, which means 80% of the text of the first document and the second document is matching with each other. And term frequency, inverse document frequency, that also a measure to do or to understand how much similar both the documents are. We'll see that with a formula. Word similarity, minimum number of operations to get from one word to another. So the Levenshtein distance measure, it is also similar like Euclidean distance measure, wherein we are finding out the distance between the first vector value and the next vector value, which is represented in a 2D plane. But here it is going to understand the minimum number of operations to get out of one word to another. So that could be done using Levenshtein distance measure. So some of the operations of Levenshtein measure are delete a character, insert a character, mutation, change the character. So example here, kitten is a word, sitting is a word. So if you look at that, how many words are changed from the first word and the second word? Sorry, second letter, not word. So kitten and sitting, if you look at it, there is only one letter change because sit and kit is what the main word. So sit-en, en, and this en is going to be maybe eliminated in the lemmatization process. So the base word is from only sit and kit. So here, if you look at this also, en and then in is changed, one letter change. So these are some of the one letter change. And sitting, if you look at, and this also one letter extra is added, one letter insertion happens. So if you look at that, depends on this word and this word, how many changes happened here. So if you look at that, E and I is changed and N is N and G is also extra added. So considering that, Levenshtein distance is one letter change and again one letter change and one letter insertion happens. So depends on that, Levenshtein distance of these two words giving us 3 over here. And word similarity example, how similar are the following pair of words are math. So Levenshtein distance gives us 0 value. Both are similar value. And math, there is only one letter change. So the distance measure gives us 1. And the other one is maybe A, T is matching and the 2 are missing one letter change and one insertion happened. So it is 2. And math and smash, if you look at it, Levenshtein. M is also present, A is present, T is not present, so one letter is missing. And then S is insertion and H is already there. So Levenshtein distance is 2. By that, it could calculate the word similarity between the pair of words. The document similarity used in large number of documents, and we could try out finding similar ones also. Maybe we could group them or cluster them together using document summarization method. Comparing documents need these following, because we cannot compare the document as it is by considering the whole one. We need to do some pre-processing step. One of the pre-processing is called tokenization. So tokenization, as we all familiar, the individual words are going to be divided into individual tokens called tokenization. Then after that, we would actually we have done a small exercise. I mean, I have shown you a small exercise on count vectorizer, where it counts the number of individual features and give the count as 111, or if it is more than one, it gives count as 2. So depending on the frequency, the count is going to be shown as a matrix of values. That matrix we refer it as document term matrix. So after tokenization, those tokens are going to be converted as individual column and column values, and its frequency is going to be represented down to that as a matrix that called document term matrix. Look at that. Few ways that data can be put into standard format for analysis is called tokenization. This is an example. Split them into individual words. This is an example we would consider as individual tokens. So we could do that with the use of tokenization process. How this tokenizer is going to be numerically encoded as words into vector space model. So each is going to be considered as a token, and then if we look at the encoded words are going to be like this is present the first, and all the three are not present in this word. So all the other feature is mentioned as 000. Yes, is present at the second level, so this is not there in the final token. So it is represented 0 and 00 for the other two as an example. And if you look at it, it's there in the third one. So all others are represented as 0. An example which is kept as the last one. So all others are 0. This is a step of encoding wherein it's going to be represented as a feature vector for the further analysis. The count vectorizer help us to create a document term matrix. So this we had seen in the example count vectorizer. Rows in could be considered as documents, and the columns are going to be considered as the term. The term is nothing but the tokens. So if we have a set of text, this is the first document, second document, third one, and one is fun if I give. Count vectorizer is the module which I'm calling it from SQL feature extraction model. And this fit transform is also we have seen fit and transform them into a matrix of values. That matrix is converted into data frame. If you look at it in the first document, I mean after these three sentences are gone through under tokenization, we get a final tokenized words. And out of that tokenized words, these are all the tokenized words considered. And the document first one is one, second, then this third, and all given. So considering that in the first sentence, and is not present. So it goes on like that. This is called document term matrix. This document term matrix are considered, converted as a data frame. We can just use this document term matrix for further process to represent this corpus or a set of words. Bag of words model is a simplified representation of text where each document recognizes a bag of its words. Let's say if I consider a bag of data mining, so what are all the words contributing towards data mining? When we form a word cloud also we might have seen that. Depends on the number of frequency, it's going to give us the word cloud intensity value of the particular word. Similar way, bag of words also would be formed with the use of keyword or key concept. So grammar and word order are discarded, but the multiplicity is kept. So how many times it is appearing depends on that. This bag of words model are constructed. And how do we using cosine similarity measure? There's a formula for that. A dot B dot operator is going to be performed. Cosine similarity is a way to quantify the similarity between the documents. So there are two steps involved in it. put each document in vector format as we did in the previous step. And then we are going to find out the cosine of the angle between the documents. If you look at document 1, I love you and I love NLP. So the final feature is considered as I love you NLP. So depends on that, we would represent the document term metrics for these two sentences. I is always appearing in the first sentence, in first document 1. Love is also appearing, you is also appearing. NLP is not appearing in the first document, so it is represented as 0. If you look at second thing, 1101 is represented. So by performing dot operator with the use of this formula, we have achieved 0.667 as a cosine similarity value. So cosine similarity value, if it is more than 65%, it is more or less similar. See, if you look at I love here also it is there. So 60%, 65% of the sentences which is there in document 1 and 2 are matching. So cosine similarity measures the similarity between two non-zero vectors with the cosine value of angle between them that is defined in this formula. So by using this, we can check the similarity between the document sentences, even two messages. If it is converted into active voice and passive voice, also we could identify whether the written sentences it is just paraphrased in a different form. Also, we can identify. Some of the document similarity examples are given here with 5 set of different documents. I just randomly calculated out of these. Maybe the 00 which gives or which shows that there is no similarity between these two sentences. See, there is no similarity between two sentences because there is no such word appearing in the first and the same in the second also. So it represents 00. It represents 0.2, maybe some 2%, 20%, 28% is matching between two documents. So it goes on like that. The other one, I mean, term frequency or inverse document frequency, there's a formula for that. Term frequency and inverse document frequency is like a different value for every document or the term combination, which means which is appearing on the first as well as in the second word. Term frequency, term count in the document, it indicates that. And inverse document frequency is just a log product of that. Total documents plus 1 divided by documents containing the term plus 1. This is also, I mean, it's a formula, it's available on the internet. So term frequency, recording the term count. This is an example. So we just record the individual terms. If there were two documents, one is very long and one very short, it would be fair to compare them by word count alone because we need to go for sentence level or n-gram method. If a small paragraph maybe of 2 sentences representing the entire set of one full page document, maybe the abstract is alone extracted in this 2 sentences. So it is not fair when we use a word document frequency as a measure to compare 2 different documents which is of different length. So if it has some similar length or maybe 10% less than that also we can go ahead with comparing word frequency level. But we cannot go with when there are more difference between total count. What is the advantage of term frequency and inverse document frequency? Assigns more weight to rare words and less weight to the commonly occurring words. So this is what it does in term frequency. So we would like to avoid for that. We go for that inverse document frequency also. So it tells us how frequent a word is in the document related to its frequency, the entire corpus, how it is appearing. And tell us that the two documents are similar when they have more rare words in common. That can also be considered in inverse document frequency. So most probably we would go with inverse document frequency also when there are rare words which is common between two documents, and we would like to go for some relative frequency of such kind of words also. We would go for inverse document frequency formula. That's all for today. Maybe these term frequency and exercise of pre-processing, I would share it with you. And in the next class, I would discuss about
Ambika, can you
regex as well as yeah, please go ahead.
can you explain one example for TF, IDF, and cosine?
Yeah, can we just I need to search for that. It is in system, but I need to search for that. Can I do it in the next class, in the first itself?
Yeah, sure.
Okay. Like cosine similarity and the other thing, I would like to show the code, right? Let me check. Just hold on. Similarity measures and so.
Can you please share this Python code file?
Yeah, sure. I will share it. See,
Thank you.
if you look at it, this are the process of vectorization, wherein the sentences what is available in the corpus are counted and then mentioned as a document term matrix. See, after the document term matrix, let's say I would like to go for cosine similarity analysis. I have given there are two sentences. The weather is hot under the sun, and I make my hot chocolate with milk and one hard coding. These are all 5 sentences which I gave. So if I just run the cosine similarity or document similarity, just for example, just give 5 rows and 11 columns. I just printed the result of the cosine similarity between the set of maybe individual sentences, but I define them as individual documents. So from the pair, it just make combinations. It takes first two documents and then calculates the cosine similarity of it. If we look at it, A index, B index, because each document has certain number of words in it, tokens in it, so that is followed and run under a for loop. And then it is just displaying, forget about this. So it just display the results. We look at the array. The first 2 pairs are giving us 0.28 and the second 2 pairs giving us 0.40. And the third one I need to check what is the error in it. Fourth one gives us 33%. This is the cosine similarity value. How it paired up and which document it is taken, maybe I'll just try to display it in the next class. I'll make it a little more simple also, these code to pair up, to show the simple sentences and then show the similarity between the sentences.
So I have only one doubt.
Okay.
Yeah, Ambika. So
Yeah, go
actually,
ahead, please.
so you explained the cosine similarity, and we have to explain the TF and IDF. So I think cosine similarity we are
Yeah.
using to, yeah, we are checking the similar of the two words, yeah, sentence. So according to that, they are
Yes.
giving us some percentage of probability. So these two words are about
Yes.
75% probability have both are similar. And
Yeah.
TF-DA, and another method we want to check
Yeah.
the both sentence are similar or not. So we are also using a TF and IDF method.
Yeah.
So
See, that
what
is
is the
for, see, word
yeah,
similarity, like document either or sentence level also you can go for cosine similarity. Okay,
okay,
this is term frequency. Cosine similarity is going to identify how the first word which is in the first document and how the first word which is in the second document are they like any matching level are there. Okay, but term frequency is work based on the word count, how many number of words which is present in a particular document and how many number of same words which is present in the second document. So word count is term frequency, like the term indicates token frequency. So it's going to count the number of tokens, depends on that frequency value only it will work. But cosine similarity it is just matching the uh, two words and then taking up, as you said, the probability, how much it is probably matching, it gives you the answer. This is different about the count, that is about the words.
okay, thanks.
Is it okay? Under document similarity, we can use any of these and then do it. This maybe you could need to go for word tokenization and then only you can apply the term frequency. But cosine similarity, as you just find out the two different documents cosine similarity, it is applicable. Is it understood? Any more doubts?
So, Ambika, you would be sharing these codes over that group or you will be sending a mail?
However, you wanted to, maybe I'll ask Shashi to do that. I can share it in
It
the group.
could share it over a shared drive, or we can definitely get that shared drive link.
Yeah, sure, I'll do that. And anyway, I need to pass on some assignment tasks also for the pre-processing alone. That as well as this also, I can share it in the drive. Sure, I'll do that.
Okay.
Okay, so to wrap up today's session, we just run through simple codes for pre-processing technique like tokenization, lemmatization, chalkboard removal, and a small amount of regex things and engrams also. And the POS tagging, parts of speech tagging, also we have run through code. Only NER is pending. Named entry recognition, we would see it later. And we have gone through text similarity measures and some of the measures which was used worldwide to check the document similarity as well as sentence similarity is also discussed. So for this text similarity and word as well as document similarity, I'll teach you some of the smaller codes in the next class, as well as we can discuss about regular expressions also in the next class. So for the next class, the agenda would be like text similarity measures code as well as regex, regular expressions. Thanks everyone for joining today's class. See you in the next class.